Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. This is our presentation from Group 7, Section 2. Today, our group are going to present to you about the project of Advanced Thermodynamics. So, there are three members of this group, which is me, Muhammad Rifan bin Abdul Rahim, and my friends, Muhammad Nazmin bin Muhammad Nizam and Muhammad Redha Slamat bin Abdullah. So the introduction of this presentation. So I'm going to tell you about the definition of thermodynamics or advanced thermodynamics, which is focused on the ideas of heat, temperature, and the interactions between heat and other types of energy. And the behavior of these values is governed by the four laws of thermodynamics, and which also give a numerical description. And the term thermodynamics was first used in 1749 by William Thomson. So I'm going to share with you three cycle, which are Carnot cycle, Breton cycle, and Rankine cycle. So for Carnot cycle, it defined as an ideal reversible closed thermodynamic cycle in which the working substance goes through the four successive operations, which there are four operations to complete the Carnot cycle, which are isothermal expansion to a desired point. The second one is adiabatic expansion to a desired point, and the third one isothermal compression, and the lastly the adiabatic compression back to its initial state. So the GIF below is the process and PV diagram. The second cycle is Brighton cycle. So it defined as since both contemporary gas turbine engines and air-breathing jet engines are constant pressure heat engines, the Brighton cycle is used to characterize their thermodynamics. And the Brighton cycle in general explains how a constant pressure heat engine operates. Instead of a gas turbine and a gas compressor, the original Brighton engine had a piston compressor and expander. So there are two types of Brighton cycle, which are open Brighton cycle and closed Brighton cycle. So the GIF below is shown the PV diagram, the TS diagram, and the Brighton cycle itself. And the third one is Rankine cycle. So it defined as sometimes known as the Rankine vapor cycle, is a thermodynamic cycle that changes heat energy into mechanical energy. And it is named after William Johnson McQueen Rankine, a Scottish engineer and scientist best known for his studies on the thermodynamic characteristics of steams. So there are four stages that describe how the Rankine cycle works, which are isobaric heat transfer, isentropic expansion, isobaric heat rejection, and lastly, isentropic compression. So the GIF below shows you the TS graph and the Rankine cycle itself. Muhammad Redo?
Okay, and now I want to present about our discussion. So from this question, design a steam power cycle that can achieve a cycle thermal efficiency of at least 40% under the condition that all turbines have isentropic efficiency at 83% and all pumps have isentropic efficiency of 65%. Prepare an engineering report describing your design. The report must include but not limited. Okay. For the question A, discussion of various cycle attempts to meet the goal as well the positive and negative aspect of our design. B, system figure and TS diagram. We labeled state and temperature, pressure, enthalpy, and entropy information for our design. And C is sample calculation. Then next, uh, For the answer for A, reheat Rankine cycle. Reheat Rankine cycle are superheat Rankine cycles that employ two turbines to enable low pressure condenser operation while still maintaining extremely high quality at turbine effluent. Benefit of reheat Rankine cycle. First, high thermal efficiency. Second, reduce peak water pump power. Uh, Third, small condenser. Fourth, small boiler. Fifth, long life of the turbine. And sixth, less handling of the fuel and firing requirement. So from this figure, can see figure of reheat Rankine cycle, and the equation for this reheat Rankine cycle is uh, Q Q in, that is heat addition, uh, is Q primary plus Q reheat, and uh, H3 minus H2 plus H5 minus H4. Then for W turbine out, there is W turbine 1 plus W turbine 2 equal to H3 minus H4 plus H5 minus H6. Okay, that's all for me.
Alright, thank you, Mr. Rido. And for the system figure of this Rankine cycle, so this is our system figure, which we have the boiler where the heat is supplied, and then goes to the turbine where the work output in charge, and then the condenser where the heat is rejected or heat out, Q out, and then the pump where the work input is. And then this is our TS diagram for the reheat Rankine cycle, where as you can see, start from 1, go through 3 and 4, where the heat supply and then heat rejected, where it goes into this cycle. And then for the next slide, alright, so the sample calculation. So given the minimum thermal efficiency of the cycle is 40%, so the thermal efficiency is equal to 0.4, and the isentropic efficiency of the turbine given is 83%, so it is equal to 0.83, and the isentropic efficiency of the pump is 65%, and it's equal to 0.65. And then the isentropic efficiency of the turbine also can be written as T3 minus T4 over T3 over T4 equal to 0.83. And similarly, the isentropic efficiency of the pump also can be written as T2 minus T1 over T2 minus T1 equals to 0.65. And if we denote S for the entropy, H for the enthalpy, P for the pressure, T for the temperature, and then the efficiency of the cycle also can be written as net work done over heat supply. And then it equal to 0.4 equal H3 minus H4, H2 minus H1 over H3 minus Hz. And if the specific heat at constant pressure is the same for all pressure, then T3 minus T4 minus T2 minus T1 over T3 minus Tz equals to 0.4. And next. Alright, for the conclusion, to conclude, the steam Rankine cycle is one of the highest utilized type of thermodynamic cycles for electricity production in the world. The steam power station run on Rankine cycle using steam as a working fluid. The simple idea of Rankine cycle is in fact the most basic vapor power cycle. This ideal thermodynamic cycle consists of 4 main components: an ideal pump that works as isentropically and adiabatically, an ideal heat exchanger system for vapor generation, a turbine operating isentropically and adiabatically, and a condenser without pressure loss and infinite heat transfer phase. And if we analyze the effect of reheat cycle over the thermal efficiency of the Rankine cycle, we will conclude that thermal efficiency of the Rankine cycle will be improved by adopting the concept of reheat cycle. But we must note that the improvement in thermal efficiency of the cycle will be very small. Concept of regenerative Rankine cycle with feed water heater will provide better positive result in respect of increase in thermal efficiency of the Rankine cycle, or in a simple way we can say that thermal efficiency of the steam power cycle will be improved quite good by using the concept of regenerative Rankine cycle with feed water heater as compared with reheat cycle. So that's all from us. Thank you.